University in Bridgeport and Rocket Center. We do a lot of training for machining, technology programs, quality initiatives, composites, work a lot with NASA, Department of Defense, work a lot with Eric, or try to, with the university. We also work with WVU, robotics lab in Fairmont. There's some literature out on the table if you want to take a look. There's a couple of videos out there. Take one with you. It's a little 10-minute DVD. Kind of gives you a good idea of our background. My job has been this development, bring in business into West Virginia, into the technology areas, aerospace, Department of Defense, NASA, the high-end skilled jobs. We trained 150 staffers for a composite project for NASA about 7 years ago. We do a lot of CNC programming, training, CAD, CAM, Master CAM, blueprint reading. So we're the government, we're here to help. And Senator Byrd started this organization about 20 years ago. We just had our 20th anniversary. There's a sheet I'm going to pass around, and if you'll just check by your name. If your name's not on it, back page, you'll fill it out. If you'll put your email address on it, then we can email you directly, because we're going to have 4 of these series around the state of West Virginia. It'll be different topics, different speakers. It's all nanotechnology driven. So with that, Eric.
Thank you, Tom. I'd just like to thank everybody for coming. This is the initial seminar of our series. And I'm very proud to present Dr. Craig Friedrich as our first speaker. He's going to talk about the economic potential of nanotechnology. Dr. Friedrich has over 20 years broad experience in micro and nanofabrication with an emphasis on integrating biological materials with nanomaterials and electronics. He got his PhD in 1987 from Oklahoma State University. Currently, he's a professor, associate chair, and director of graduate studies in the Department of Mechanical Engineering, Engineering Mechanics at Michigan Technological University. He also holds the Richard and Bonnie Robbins Chair in Sustainable Design, and he's also the director of the Multi-Scale Technologies Institute at Michigan Tech University, which is part of a NSF Nano sponsored center. And he also leads the Multi-Scale Sensors and Systems Research Group. Craig and I have been working together for about the last 3 years on different sensing technologies for the diagnosis, monitoring, and treatment of chronic disease. He also has an extensive manufacturing background, and today he's going to talk a little bit about the economic potential of nanotechnology industry.
Thanks, Eric. The title, I hope, won't be too misleading. If I had the answer to that, I wouldn't be a state employee. So what I'd like to do would be to share with you just a few brief comments and a very broad oversight about some of the potential areas that nanotechnology might be able to make an impact sometime in the future. So I'm from the other almost heaven, as we call it, very similar to the West Virginia scenery, lots of natural beauty, rural area. The only major difference is we get about 22 feet of snow every winter. We're situated right on the southern shore of Lake Superior, and starting here next month, unfortunately, those cold Canadian winds will be coming down and picking up that nice warm lake water, and our first snowfall is typically late October. So I'm certainly happy to be here before we get snowed in for the winter anyway. So I've broken my talk into 4 basic areas, 2 potential areas for nanotechnological impact in energy and healthcare. We certainly cannot ignore what is turning out to be a growing legitimate concern about the side effects of nanomaterials. And so I want to keep this informal if I can. So to begin with, being an engineer, I'm going to put out and talk about a lot of numbers. a lot of units, microns and nanometers and so on. So I always start out trying to get down some comprehension, if that's even possible, of the size that we're talking about. So a micrometer or a micron is 1/1,000,000th of a meter. A meter is just over a yard, about 39 inches or so. But that doesn't mean a whole lot because I don't know what a million means. I don't even know what a million means, so I don't know what 1/1,000,000th can possibly mean. But 25 microns is about 1,000th of an inch. Now we're getting into maybe manufacturing tolerances. Plus or minus 1,000th of an inch is plus or minus 25 microns. 100 microns is about the diameter of a hair. I used to walk around the lab pulling hair from my graduate students and measuring them, and it varies between 80 and 100 microns in diameter, and 100 microns is also the thickness of an average sheet of notebook paper. So that gives you some scale. Now a nanometer is 1,000th of a micron. So that means there are 100,000 nanometers in the diameter of a human hair. So think of a hair and cutting it across the diameter 100,000 times, and that's the nanoscale. The spacing between atoms in a solid is a few tenths of a nanometer. So when you're down talking nanometers, as we will be, you're talking down at the atomic and molecular scales of materials. So before we can talk about nanotechnologies, let's go back and still summarize a little bit about microtechnologies, because those are still extremely pervasive in all of our lives. This is the Babbage difference engine. If you remember the movie Rain Man, his brother was Charlie Babbage. So this is a difference engine. This is a mechanical computer that was designed by Charles Babbage in the 1840s. This one wasn't actually built until 1990. This is in a museum out in Santa Clara, Silicon Valley. It's about 6 feet high and about 8 feet long, just to give it some scale. It's a huge, heavy piece of mechanical computing. And it's able to solve polynomials up to the 31st order. And it's also able to print the results. This was designed in the 1840s. This is a replica of the first transistor from the late 40s at Bell Labs. It doesn't look like much. I always tell my graduate students, I'm an experimentalist, so are my graduate students. They always like their experiments to be aesthetically pleasing. I say, don't worry about that. Look at the picture of the first transistor and think about what impact that has had on the world. And it's one of the ugliest contraptions you could ever think of. But now we're putting more than 800 million of those onto a single chip in a PC. A teraflop, if you're not familiar with that terminology, a flop is a floating point operation. It's the most fundamental arithmetic operation that a computer performs. Tera is 10 to the 15th. I'm sorry, 10 to the 12th. 10 to the 12th operations per second. So in 1996, this is what it took to perform 1 teraflop of computing. 11 years later, it's down to the chip scale. So this is the very rapid progression of microtechnologies, Moore's Law, and so on. And there has been a tremendous boom, not paralleling computing in silicon, but mechanical and electromechanical devices in silicon. The field referred to as MEMS, microelectromechanical systems, non-integrated circuit MEMS. It's mature and it's pervasive. It's used in inkjet printers, the print heads in inkjet printers. The accelerometer or accelerometers in your automobile have moving parts of silicon, and they're electromechanical. They have a proof mass. They have interdigitated fingers. One set is stationary, the other set is free to move on springs. The proof mass, if you decelerate too quickly in the event of an impact, the change in the coupling capacitance, the rate of change in the coupling capacitance triggers what that deceleration level was. And within milliseconds, the onboard computer must decide whether to deploy that airbag or not. There's no assembly. That is all done from a solid piece of material by chemical etching processes. So in consumer electronics, in your Wii and so on, there are gyroscopes and accelerometers in there, tire pressure sensors, disposable blood pressure sensors, all MEMS technology. I didn't look at this Epson projector here, but digital light processing. That chip, a DMD chip, has many, many thousands of individual mirrors, each maybe 10 to 12 microns in size, that are capable of flipping at very high speed to either project light or to baffle light internally to create programmable movies and programmable displays. BioMEMS and lab on a chip, which I'll talk about in just a little bit. So all of these are micro scale, not nanoscale, but micro scale. Now, part of electronics is certainly now down at the nanoscale, and that's part of its limitation, is the amount of heat that is generated by conventional CPUs compared to the amount of energy that they consume is going up and up and up and up and up. So now in computing, the problem is cooling, because the dimensions of insulating films are getting so thin that leakage current is becoming the dominant energy consumer, and that leakage current is nothing but waste heat in a CPU. But the global market for these MEMS products this year is about $72 billion. So that's every year, and it is still growing. Now, MEMS started about 30 years ago. The first silicon micromotors were demonstrated about 30 years ago. So it's taken that long to reach this level. So this technology does not happen overnight. There are very few technologies that do expand as quickly as microelectronics have expanded overnight. Those are the disruptive technologies that everybody hopes for. Lab on a chip. This is now not mechanical and electrical integration, but this is fluidic and electrical integration, where you are capable of performing benchtop type chemical analyses on typically a plastic chip, a microfluidic chip that will contain pumps and valves and reagents, and electrical signals are input and results are output. And these large bench scale analysis systems are now being shrunk down to much smaller dimensions. So nature has been using nanotechnology for a very, very long time. Diatoms, microscopic critters, animals, organisms, are capable of creating order out of inorganic materials found in their environment. And they're capable of doing that with very high precision repeatability. A clam shell is made up. It is a beautiful, beautiful composite material made up of extremely hard, thin phases that are joined together by highly elastic and tough proteins. You know what it's like to try to break a clam shell. A beautiful natural material. Department of Defense has been looking at that for materials such as armor, because it has exceptional toughness in addition to exceptional hardness. And this scale bar here is 4 microns, so it gives you some size scale there. So is 4 microns larger or smaller than a hair? Oh, quiz time, okay.
Smaller.
Yeah, smaller. So a hair is about 100 microns or so. Well, we can do funny things at those scales in different materials as well. This is an optical waveguide in a solid material. The scale bar here is about 3 microns. Well, what's all this about? Well, these patterns in an solid state optical waveguide are able to effectively reduce the speed of light in that waveguide. So right now, we do not have electronics that can operate at the frequency of light. They do not exist. If you can slow that light down, its frequency will also go down. And now you can start manipulating that light and integrating it with electronics. For example, this structure could potentially be used for an optical gyroscope, where you literally have beams of photons going around in a ring. And that ring only needs to be about 100 microns in diameter. And as that ring rotates, the relative speed of those two counter-propagating beams of light change phase, and that can be measured. But we must be able to measure it at the frequency of that light, so we have to slow the light down. Zinc oxide nanotubes are being looked at for something referred to as dye-sensitized solar cells as a substrate, a conductor, in a non-silicon-based new class of photovoltaics. This scale bar is 300 nanometers. So 100 microns, the size of a hair, is about 300 times that scale bar. So, I don't know what that is. We'll just call it 4 inches, maybe a third of a foot. So at that scale, a hair is 100 feet in diameter at that same scale, just to give an idea of size. So we can fabricate down at those scales. The key is doing it economically and finding, as they call it, the killer app. We know how to do things, we just have to figure out what to use them for. That's one of the larger problems. Well, folks through antiquity knew what to use the materials for, but they didn't know what the materials were. As far back as ancient Rome, they would impart colloidal gold or gold into the materials. This cup is being lit from the interior, and it's got a beautiful change of red or rose to purple. That's the presence of nanomaterials, nanoparticles within the bulk of that cup. If you take that light away, it's just a very dull drab green. That's all it does. The old stained glass windows, those different colors, nanoparticles within the glass. So people knew what to do and how to do it, but they didn't know why it happened. So now we're closing that loop in the field of nanotechnology. Michael Faraday, electrical induction, 1856, his very young logbook. He had gold nanoparticles in a solution. And as he noted, it gave a very fine red fluid. He didn't have microscopy to determine why it was that color, but modern instrumentation, we can correlate the color with the size of the nanoparticles and the way they interact with light. So what are the roots of modern nano now? Well, it probably started in 1959 with a challenge by Richard Feynman in a talk at Caltech titled, "There's Plenty of Room at the Bottom." Feynman later won the Nobel Prize in '65. He was a physicist. He won it in particle physics, but he set forth a challenge. Of course, the atomic bomb had been developed. Nuclear physics was in process of being further understood. He laid down the challenge that we should be able to manipulate matter at the atomic scale. That there is plenty of room from where we consider small to be in 1959. There's many orders of magnitude of room at the bottom, and we should be able to manipulate matter at those scales. And of course, since then, there was, until Richard Smalley died, there was a large sort of public feud between Richard Smalley, who won the Nobel Prize for nanomaterials, and Eric Drexler, who was more a proponent of nanotechnology being built one atom at a time from the ground up. Smalley said, no, you can't do that. Number one, we don't have the technology and the science to do that, or the knowledge how to do that. And number two, it can never, ever, ever be economically justifiable. And they publicly debated in the journals back and forth. Of course, Richard Smalley died here a few years ago, and so that debate has very much died down. In the mid-'80s, IBM developed the probe microscope. The first two, the scanning tunneling microscope, the atomic force microscope. There are many incarnations of probe microscopes, but they're able to manipulate matter at one atom at a time. They use a microcantilever that's got an almost atomically sharp tip. They can pick up a single atom of xenon, transport it over, and put it onto a smooth surface of nickel. And they did that, and they spelled in atoms the letters IBM. This was in the mid-80s. Well, what are some of the areas where nanotechnology is in the market now? And perhaps we may not be aware of it, maybe we are. This is a rather contentious application using a material referred to as nanosilver. Silver is a natural antibacterial material. It will kill up to 650 different bacterial types or species. A company developed a line of appliances, a washing machine, a dryer, and a refrigerator that incorporates nanosilver. The idea there is that when you wash your clothes, nanosilver is left behind in the fabric. It's naturally antibacterial. Reduces odors from the material. Well, the one problem that was realized is, well, there's a lot of that nanosilver that goes out with the wastewater. And it can kill bacteria within the municipal wastewater system. And not all bacteria are bad. There are a lot of good bacteria out there. So actually they took it off the market for a short time, and now it's back on. It's on the market. Nanoelectronics, or organic electronics, using a process referred to as dip pen, or highly parallel dip pen lithography. Think of thousands and thousands of quill tip pens, and each one is nanometers in size, depositing nano droplets of conductive or semiconductive inks. So now you can start writing electronics on nearly any underlying material that you want. That's a company. Oh, probably about 8 years ago or so, a new technique was developed for detecting at extreme sensitivity or very high sensitivity the presence of potential disease markers. This is some of the first work that was done. And the inventor of this claimed about a 1,000,000-fold increase in sensitivity over currently available lab-type techniques. And the application sought for this was in sensing prostate serum antigen, a potential biomarker of prostate cancer. Well, this device was apparently so sensitive that they were sensing PSA in women. And they weren't quite sure what that meant. Is it really there? Or are we just fooling ourselves? Because this is so sensitive. Are we getting some false positive indication of that being present? And of course, as if you followed the news last week now, there's a whole school of thought within the medical community that says don't worry about that anymore. That potentially not the actual blood test itself, but any subsequent probing or investigations could be worse than the disease itself, because it's such a slow growing type of cancer. The car companies use nanoclays in paints and finishes. These materials make the finishes much harder and much more scratch resistant. For example, GM uses about 300 tons per year of nanoclays mixed in with car finishes. And I'm not a golfer, but nanofibers, carbon nanofibers, are used in handles of tennis rackets, golf clubs, and so on. I couldn't begin to tell you whether they do any good or not. Anybody in here play golf? Have you experimented between them? So I have no opinion on that whatsoever. So nanotech and energy. This might be a little farther outlier of where nanotech could potentially be used. But again, who has that crystal ball? Who knows that? So this is a dated slide. It's 1999 from Lawrence Livermore National Lab. But the numbers aren't that important. It's the relative relationship or scope of the numbers that are important. Here on the left side, what they did was to take all types of energy input. This is here in the US. All types of energy input that are used. Nuclear, hydro, biomass, coal, and so on. And they kind of trace them through. And then here is the output of all that input. A certain amount of useful energy and a certain amount of rejected energy. Now, if you're a mechanical engineer or if you've had a course in thermodynamics, you'll know this word. A Carnot cycle is a thermodynamic cycle that is 100% efficient. There are no losses, thermodynamic losses within that cycle. It's an idealized cycle. Well, if you look at the amount of energy rejected from waste heat in power plants and automobile engines or whatever the case may be, and relate that to the amount of useful energy, you come up with an overall energy conversion efficiency of about 41%. What that means is we take all of the energy in the US that we utilize, and the average TH, the average high temperature of all of that energy conversion is about 435 degrees Fahrenheit. That means we're putting a tremendous amount of energy, thermal energy, into the environment, and it has nothing to do with greenhouse gases. We're using all that energy at 435 degree average temperature. So that can be a tremendous energy source in global warming. Now, if we look up here, well, where does some of that energy go and where does some of it come from, and what might be some alternatives to that that don't operate at those high temperatures on thermodynamic cycles? Well, there's more solar flux per hour hitting the Earth than we use in the energy from fossil fuel in 1 year. An incredible amount of energy, solar energy, strikes the Earth. The one problem is, it is at a very low potential, or thermodynamicists would call it low availability. It's like trying to drive something at 1/10 of a volt potential. Things don't like to move because there's not much of a driving force for events and processes to happen. And that's one of the problems with solar energy, is it's pervasive. There is so much of it, but it's at a relatively low potential above the background. And so things don't operate vigorously off of solar energy unless you can get a lot of it and you can concentrate it. We spend more money per hour in gasoline than we've spent in solar R&D the last 6 years. So there is a lot to be done in looking at how any technology, in addition to nano, can be brought to bear on these problems. So I'll talk about solar for just a brief minute. As of now, to date, the maximum record efficiency of any solar cell is about 42%, just over 42%. And that has taken since about 1975 to get there. That's 35 years. To get from down here at general range of 10% up to 40%. And these 40% solar cells are very expensive and complicated solar cells. They use a lot of metals, strategic metals, that we have to import, or the manufacturer has to import from around the world. And we need to start looking at being more self-sufficient and not relying as much on those strategic materials as we have in the past. Because as we know, the politics of the world can change very quickly. There is a new emergence here, down here, low efficiency, but then it really didn't start until about 2000 or so. And that is in dye-sensitized solar cells and even bio solar cells. Just go outside. All those trees out there know how to convert sunlight into energy. There are a lot of microorganisms that convert sunlight into electrical charge directly. And so there is a tremendous amount of biodiversity out there that has learned how to convert sunlight very efficiently into chemical and electrical energy. But you can't always depend on the sun, and this is one of the stumbling blocks. This is really a very busy graph. I only want to make one or two very brief points here. If you take a spectrometer and point it at the blue sky, the solar power that it receives peaks here at nearly in the UV. Well, that's why the sky is blue. It's down on the blue end of the spectrum. If you point it directly at the sun, the yellow curve, that peak occurs here in the mid-visible range of the spectrum. Don't worry about the amplitudes or the heights of these things. That has no significance right now. So if we're going to design a solar cell, and we can't just design the material to do what we want it to do, even though we can try that. Materials just don't work that way. We're pretty much stuck with what we have, stuck with what we can alloy and blend and put together, and try to tailor the properties the best we can. So if we design a solar cell that likes to look at the blue sky and scavenge the maximum amount of energy, it's mostly efficient looking at a blue sky, we're going to be pretty far away from if it's looking directly at the sun, which is yellow compared to the blue sky. If we look on a cloudy day, the gray, it pretty much maps what the direct sunlight does, because the direct sun is coming through the clouds. We were looking at the sun through the clouds, but in that case, that gray curve is going to be way down here somewhere. So if we try to average out everything, because this thing is just going to be sitting out there in the environment, in the weather, what we have to do is to try to come up with a material or materials that will operate over a much, much broader part of the spectrum. And that's what those most efficient solar cells do. They are what's called multi-junction solar cells. There are multiple solar cells where light goes through the upper one, scavenges its optimal wavelength, goes on down, the next layer scavenges its optical wavelength, optimal wavelength, and so those are very expensive to make. Well, what about wind? Because the sun isn't always there, and that's one of the problems. It's only out there at best 12 hours a day. Wind, unfortunately, where the best sources of wind are, the coast, is not where the transmission lines are. Because you don't live in the water off the coast, you live inland. So if you're going to generate wind, you have to be able to distribute that more. The sun shines everywhere. You can put a solar panel on your roof. It's local. But the wind doesn't blow everywhere. So you have to capture the wind where you can and distribute it through the systems. So the coasts, we're up here pretty good too. The wind blows a lot in upper Michigan, right on the coast. But we don't have many people up there. We have to transmit that electrical energy down to where population centers are. And that's the major reason that T. Boone's Pickens venture failed, is the cost of getting the energy away from West Texas was just too much. It just didn't work. But the problem is the wind doesn't always blow either. So if we don't have continuous energy generation that we have with fossil fuels, if we're starting to rely on alternative fuels, solar and wind, for example, we have to be able to save up for a rainy day, so to speak. We have to be able to store that energy, because having those alternatives sitting on top of a grid is not necessarily the best answer, because those sources fluctuate not with predictable daily use as energy consumption does, but rather predictable with the weather. Right now, the utilization of alternative energy is really a matter for utilities of trying to predict the weather. When's the wind going to blow and when's it going to be cloudy? And that's something that companies aren't, that's too much of a variability. Something companies aren't yet willing to put into their mainstream models. So they're treating alternative energy literally as energy sinks and not energy sources, sitting on a smart grid. But some work has been done in trying to create supercapacitors and batteries using carbon nanotubes. Those devilish things that we hear so much bad press about, carbon nanotubes. Whether they work well or not, they work better than conventional batteries, but they don't have the capacity. They can quickly charge and discharge, but they don't have the overall capacity that conventional batteries have. By the way, that's a 100-gram sample of carbon nanotubes. 100 grams is less than 4 ounces. Takes up that because they're mostly empty space. Okay. Also, carbon nanotubes, good pure carbon nanotubes now cost about $12,000 a pound. Pretty pricey if you're going to make batteries out of them. Lithium-ion batteries can charge and discharge very quickly and yet with good total capacity because they use nanomaterials in the electrodes. More surface area at the nanoscale, charge can transport at a much higher rate into and out of the internal of the battery, into the electrodes, and into the outside world. Batteries are now being looked at as grid stabilization systems. Store during the day or use it when the alternative energy sources, if it rains, if the wind stops blowing, you have extra capacity that's now been stored. Again, costly, very costly at this point. Plug-in hybrids and plug-in electric vehicles. Being up in Michigan, we're very well tuned into the auto industry. Utilities are chomping at the bit to have 1 million electric vehicles plugged in during the daytime at the shopping centers and parking lots and the business offices, because then when they see demand go up, little spikes in demand, they're not going to ramp up their turbines because it's got such a lag time. They're controlling the grid. They're going to pull power out of all those batteries in the vehicles. And then when the spike goes back down, they'll recharge. So it's a net zero. It's load leveling. But now the battery manufacturers, the automotive manufacturers say, no, we're never going to guarantee our car or our batteries to cycle like that. We test it in a driving environment. We don't test it as part of a smart grid that's going to make up energy when there are demand spikes. So it's a big, interesting conversation going on now between utilities and battery manufacturers. And if nothing else, we need to get these people the load off of their backs. This is a Navy SEAL. They typically carry 150 pounds of gear. Half of that is food and water. 2/3 of the other 75 pounds or 50 pounds is batteries. They're intelligent platforms, or they're platforms for intelligent weapon systems. GPS, radio, infrared, all those things. You know, those pictures, those infrared pictures we see on the news is not a huge extension cord behind the soldier. That's all battery power that they're having to carry. And so DoD has invested heavily in new battery technologies. But now there might be some alternatives looking at biology. We like to think we're at the top of the food chain, that we're very sophisticated and so on. Well, for us to go from the ultimate provider of energy, the sun, down to our, as we sit here, each one of us expending 150 watts of power, it takes about 8 steps for that entire process. Now, if you're a vegetarian, you can bypass just a couple of those steps. But still, we are having to get our energy from the sun in a very complex process. Well, life has learned how to bypass all of that at the microscale. There's bacteria that can take sunlight and convert it directly into electricity. And there are myriads of bacteria that can do that. If you ever see pictures or fly over San Francisco, the Bay Area in the summer, you might see large ponds, swamps that are purple in color. That's one of those types of bacteria. And so what can happen is this little critter, which is only a couple of microns in size, can take that sunlight and through a very simple and very efficient process convert it to a separation of electrical charge. And that's exactly what a solar cell does. This bacteria grows in ponds. It's pond scum. The pond has to be very salty, but it's pond scum. And so you can work with this bacteria. It's very easy to grow, and because it grows in ponds, it doesn't take all that much care. So we've grown it up, and it takes a few days, and you let it multiply and multiply, and you extract the cells, and you break the cells open, and you literally take the cell membrane of this little bacteria and break it into pieces, and now you can treat it like little tiny solar cells. And you can deposit that onto a surface, you shine light on it, and you can create charge, and you can create current. One problem is, if you want to buy this on the open market from a chemical supply house, it's about $450 a milligram, not very cost effective. Well, we can make it for $2.41 a milligram. Quite a cost savings. Now, that does not include labor. And this is one of the beautiful things about being at a university. Labor is very inexpensive. It's called graduate students. So a lot of work can get done at very low cost. The whole key is converting that over to a business model that will be successful. But if you take that, what's called bacteriorhodopsin, and we put it on a glass slide and we hook electrodes up to it and we turn the light on and off, we're generating about 0.6 of a volt just by turning the light on and off on that membrane. And we're able to create current here. This is in the microamp range of current, not very much. But both of those are sufficient to power a small calculator. So you can go to Walmart and you can buy a solar powered calculator. Anybody seen those yet? $1. $1. And the solar cell in there, if it was bacteriorhodopsin, would be about 1/3 that size. But the cost of developing that technology. So I'm just going to skip this. Well, let me mention, this optical protein we've also used, or can be used, in a sensing technology. If you can disrupt that light to charge process with some type of binding or sensing of a toxin or material, now you've got a chemical sensor. Well, you can shine a light on it, create power, and at the same time it can be used as a sensor. So it's a self-powered sensor. Just all you have to do is shine some light on it, and it's sitting there, and if it binds with something, it will disrupt that chemical process. The signal shuts down, and you can sense that as that toxin being in the environment. And you can take this down to the nanoscale. These are nanotransistors that have been regulated, modulated with this protein. So it's a very, very versatile nanoscale solar cell that is very renewable. You grow it and grow it and grow it, like pond scum. In fact, it is pond scum. And here's some sensing work that was done in sensing maltose, one of the most basic sugars, a very safe toxin, if you will. But it works very, very well. So this is probably going to be a much larger sector for nanotechnology, and that's going to be in healthcare. So we want to understand the difference and the advantages of natural materials versus synthetic or man-made materials. And this is one mechanical property for anything that's going to be used in a structural type physical application. And that property is called toughness. Now, you know what strength of a material means. It's how much you can pull on it before it breaks, essentially, for a given cross-sectional area. We know what ductility of a material is. That is, how well can you bend it? How flexible is it? Well, toughness is a combination of both. It's a property of a material that can absorb tremendous amounts of mechanical energy without failing. And that's one of the keys of composite materials. Fibrous and other types of composite materials. They can absorb large amounts of mechanical energy without failing. Well, of all these materials, bone here is about the weakest or lowest toughness. It's not a good mechanical material for absorbing impacts and energy. And as you know, it's not much different from high-strength steel. So those two are similar in their toughness. But if we come down here, and these are just relative numbers, if we come down here to spider silk, it's incredible. We now understand why that is. We understand the composition and structure of spider silk. It's been estimated that if you could take and weave a rope 1 inch in diameter of spider silk, it could stop a 747. It can absorb that much energy without breaking. It's an incredible biological material. So how do we get those materials into consumer products? Well, again, a large challenge there is how do you do it economically? It must survive the environments and the usage and so on. So orthopedic implants or medical implants, us baby boomers are just getting started. So there are over 1 million joint replacement surgeries in the US in 2009. And in hips, the cost of a first was about $35,000. Well, take 35,000 times 1 million, you're up at a $35 billion annual market. That's not a shabby market. A revision or replacement is even more. Orthopedic implants last some length of time or expected lifetime. They must be replaced. So the number of hip and knee replacements is expected to double up to 4 million, nearly 4 million by 2030. So anything that can make those implants utilizing nanotechnology or any other technology more durable and have a longer life is going to be a tremendous benefit. Titanium nanotubes, not carbon nanotubes, titanium nanotubes. Titanium is a wonderfully tough material. It's used in aircraft and so on. Well, you can put nanotubes on the surface of titanium. This is a bone screw, just a short piece of a long bone screw that has nanotubes placed onto the surface. Well, each of these nanotubes are all on the order of 100 nanometers in diameter, and you can make them pretty much whatever length you want. And it turns out that osteoblasts, that's the precursor of bone, osteoblasts far prefer to grow on nanotube surface than bare titanium surface or smooth titanium surfaces. And so being able to put these nanostructures onto the surface of orthopedic implants does a couple of things. It provides a more natural environment for the cells to grow on. The cells are used to growing in bone. Bone is not a very stiff material. Titanium is a very high stiffness material. You put in a smooth, bare titanium implant where it's going to interface with bone, and the bone doesn't recognize it. The cells really don't want to grow on that really stiff surface. They want a much spongier surface because it's a natural environment. And that's what these nanotubes provide because they're freestanding tubes, they can bend. And as those osteoblasts crawl around the surface, it seems like home. And they're happy, and they grow much, much faster. Even to the point, actual experimental data. The blue here represents the number of cells per square millimeter after 24 hours, 48 hours, and 72 hours of culturing on top of various structures of titanium, pure and alloy. Plain old aircraft alloy, Ti6Al4V if you're familiar with it. The blue is bare titanium. The red is titanium nanotubes as they are fabricated. The green are those exact same nanotubes after they have been heat treated to about a 3-hour heat treatment. So what you can see here is after 3 days, the difference between nanotubes that have been heat treated and nanotubes that, bare titanium, you can see a difference of approximately 6 times the number of cells that have grown on that surface in a set period of time. So that cell growth is much, much, much faster. The cells grow because those nanotubes change the way water behaves on those surfaces. The surfaces with these nanotubes on are what's referred to as super hydrophilic. Hydrophobic means fear of water. Water beads up on a surface. Hydrophilic means the water likes to spread out onto the surface. Well, these nanotubes are super hydrophilic, water-loving surfaces. Well, cells are mostly water. Biology, our bodies are mostly water. So those materials like to spread out onto those surfaces, and that induces them to move around. So what we do is we take these cells, and we use an instrument that was actually created for the semiconductor industry to cut through integrated circuits as part of process control. So when you create these integrated circuits, it's a layering kind of process. Well, you want to cut cross sections through those transistors and look at your quality control and the thicknesses. That's called a focused ion beam system. Well, you can take that focused ion beam system and cut through an osteoblast, a precursor of a bone cell, and look at what's happening at that interface between the cell and the nanotubes, and some pretty interesting things take place. You can see that the cell is starting to migrate down into and in between those nanotubes. So the amount of surface area that that cell is adhering to is going up exponentially. If it will adhere to that surface with more surface area, it's going to be a stronger bond to that implant surface. Here's one of the filipodi, or feet, of an osteoblast. They use those to kind of crawl around in an inchworm kind of way around on the surface. It's putting out what I refer to as feelers here, to get down and probe down into the crevasses and so on within those nanotubes. And it's going to hang on to that surface with a tremendous amount of chemical strength. In fact, these surfaces will bond to bone about 9 times stronger than bare titanium. There's a very strong bond between these surfaces and bare titanium surfaces. So what's being looked at and envisioned is one application there. Now, are there pitfalls? Yes, and I'll talk about those here in just a minute. Nano is at life's basic dimensions. We are huge chemical factories, chemical machines. We have hopefully normal chemistry going on almost all the time, but when abnormalities crop up, we create abnormal chemistry and abnormal exhaust products of that chemistry. If we can determine what those exhaust products are, those abnormal ones are, early enough in the disease, we can intervene at a much, much, much earlier stage. You know, right now, many times, the first symptom of coronary heart disease is death. That's not a very good first symptom. You'd like to know something maybe a little earlier than that. So the body has many what are called biomarkers. They're chemical signatures of both normal and abnormal physiology. And so Marshall and Michigan Tech are working together in the Center for Diagnostic Nanosystems in developing nano-sensing systems to identify certain of those biomarkers. Marshall is heading up the life sciences aspect of it. We're heading up the hardware aspect of it. So the key there is, with all of these biomarkers, many of them are benign. We don't know which ones and which combinations. And so we're at the point now where technology is way ahead of bioinformatics, of knowing which of those combinations are important and which ones aren't important. We can sense them all, but we don't know which ones to sense just yet. So as I said, the life sciences research is being done here at Marshall. The hardware development is being done up at Michigan Tech. We just presented this at it's called Lab on a Chip World Congress just last month. Early work. We've already been contacted by one large instrumentation manufacturer for additional information. An example of the nano-wire chips, and I'm not going to go into all the details, but we're creating nano resistors. Those resistors have lateral dimensions of about 70 nanometers. They're just literally silicon wires. And when we functionalize or put a particular molecule on that wire that can then bind, chemically bind with what it's designed to bind to, a biomarker it's specifically designed to bind to, that will cause a change in the electrical resistivity of that wire. And that can be measured. So we're working on these systems. The brass ring someday might be similar to a glucose meter that you can buy off the shelf. But now that those test strips might be specific for specific potential diseases. We're never going to diagnose those diseases. That's what the medical community does. But we can give people information that says perhaps you need to take the next step. Environmental and health risks, we certainly can't overlook that because nanomaterials do have advantages and they have disadvantages. At the nanoscale, everything is a surface, and that can be very advantageous. At the nanoscale, everything is a surface, and that can be a disadvantage because the body will react to it very, very differently than a larger microscale dimension might be. So, 2 points here. Nanomaterials can be both man-made and naturally occurring. We have grown up with nanomaterials. Not just us in this room in our lifetimes, we the species have grown up with nanomaterials. They found carbon nanoparticles in 10,000-year-old ice core rings from Greenland, down at a depth of 1,600 feet. There are many, many natural processes that create abundant nanoparticles. There are suspected disorders related to nanoparticles, but again,